It's 5 p.m. West African time here. Welcome once again to DSN Free Mentorship Session. So like I said to our newcomers for today, I will briefly introduce to you what DSN is all about, all right? So let's get started. DSN is committed to raising 1 million AI talents and now expanding to provide solutions to enhance 1 billion lives. And this has been achieved through community, product, and partnerships. So how did we evolve? DSN evolved from learning and community to supporting startups and national development initiatives. This is huge. I want you to please be proud and be excited to be part of such an amazing community. And if you're not yet part of our community, don't worry, you're also welcome, right? Not only that, DSN being the top AI learning community in Africa, won the highest AI award in Africa, and that's the Matter Impact Award at Deep Learning in Durban 2019. We are also committed to producing world-class and award-winning papers. One of such is DSN winning the Best Poster Award at the 21st edition of the Global Economic and Communication Conference. An amazing feat by DSN is being the only African finalist at 2021 X Prize competition on building advanced AI algorithms to address COVID-19. Wow. Many of our papers and projects have been presented at top conferences and recognized by organizations like UNESCO. We had 2 products emerging in the 2021 Global Top 100 AI products. We have our product, the EdTech AI Adaptive Learning Engine, and the Prescribed Rights. Now, down to our annual report 2021, we are so excited to release our 2021-2022 annual reports. I want you to kindly like, share, retweet, and download. My colleagues here will share the appropriate links. We also unveiled a data fluency platform to be used for free. In case you don't know what data fluency is all about, data fluency is the capacity to absorb data and information to gather insights to boost decision-making process. So our business intelligence enthusiasts here, data fluency is an important part of business intelligence. So I want you to visit the link to learn how you can get started to maximize data today. DSN is also quite interested in raising the next generation of AI talents. Hence, we released the first AI and Python book for elementary students and beginners in Africa. So go get your copy, as my colleagues will also share the relevant links. Have you seen an AI research lab before? If no, then I'm glad to let you know that DSN has the physical AI research laboratory and co-working space at Yaba, Lagos. You can now apply to make use of the amazing facilities for your startup or work. DSN has been at the top of their game because they stand on the shoulders of giants. These are world-class advisory board members. Kindly drop an emoji as we celebrate our amazing board members. They are such amazing personalities. We have there our chairman, Dr. Huyi Stewart, and so on up to, we have 15 over here. So kindly appreciate them, please. So now that you know DSN, let us meet our mentor. Our mentor, Mr. Moshood Yahaya, is an AI machine learning engineer at Dial. He's a passionate and reliable professional with multiple years of experience, only dedicated to using data to provide insights and also to make informed decisions. His expertise is placed within market analysis, forecasting, business intelligence, business process optimization, revenue assurance, performance analysis, and customer need assessment. A round of applause for this amazing personality. Kindly welcome Mr. Moshood Yahaya as it takes us through clustering algorithms and its business applications. Mr. Moshood, the floor is yours.
Thank you very much, Folashewa. Good afternoon, everyone. Oh, my camera is off. Yeah, I don't know if everybody can see me now. Yeah, good afternoon, everyone, and thanks for joining us in this session to take us through business application of clustering algorithm. And we'll try as much as possible to see what we can cover in the very short and limited time that we have. I'll just share my screen, just a moment. Can you see my screen?
Yes, we can see it.
Yeah, thank you very much. Thank you very much. Just 1 second. Oh, brilliant. So basically, what we're planning to talk about today is clustering algorithm. And the simple question is, in most cases, when you need to talk about a particular concept or a business type, a business case or technology, the simple question is always, why do we even need it? Why do we need to talk about this kind of concept? Why do we need to go into it? It's usually not useful when you only talk about something because of how fancy they appear to be or how, lovely it sounds to the ears. It's usually more about the applicability, the reasonability, and how much sense it makes if, pardon my use of that word, for us to go about talking about them. So why do we really need to talk about clustering algorithm and application? Basically, most times when we start learning machine learning, sometimes we get across using data sets that are probably as clean as you have it, labeled and everything, and you end up using maybe regression algorithms. You get use of maybe some binary classification method, or use a lot of classification algorithm. But then you ask yourself, in real life, do you always have things as organized as you have it in these cases that I've mentioned? Most likely no. Sometimes you would have data sets that are actually not labeled. Not even sometimes, most times. And the simple thing is this: one of the biggest issue we have in machine learning maybe is the fact that when you're starting off, you obviously want to try as much model as possible. That's usually the problem of maybe someone who is just literally just starting machine learning. Try write code as much as you can. Then when you get to a stage, you start struggling with what kind of algorithm or model do I go about using. Then when you get to a stage, you start struggling with, do I even need machine learning? Do I even need to use machine learning? Because it's gotten to a point where we've made a magical conception about machine learning, and it's all about just give it to the AI experts, they will get a result. So, and most times, most companies talk about being data-centric, and then you find out it's only in policy. So that's why people make a lot of money from helping companies to label data, because of the little or no knowledge in the use of clustering algorithm. And that's probably the major difference between your classification model and using doing clustering. Clustering basically helps you to deal with, you're trying to analyze. I want to sound as practical as possible. So you're trying to analyze maybe purchasing power of a particular group of customer in your business, and you're looking at a way to derive their purchasing preferences from their model. Now, there's something in marketing that we talk about, the concept of segmentation. And when you segment your customer base, that helps you to now position on the particular customer you want, on how to get each segment of the customers and how to position yourself into them. So this is a typical example of what you get using clustering. You have large data set about these customers. You don't know where to start from. What do? It's about sieving them. It's like you have rice and beans packed together in a place mixed up. I mean, it takes natural order for you to know the size of rice is different from the size of beans. But then at some point, you have to sit down and remove rice from beans. That's a very, very crude example of what clustering is like. And in the example of the customer, is more like using the behavior or inherent characteristics, like in rice and beans. Beans is brown and it's bigger, rice is white and it's smaller, and it helps you to naturally differentiate between them to be able to make informed decisions as to how to manage different segments. There are different other applications of clustering that we can go into, but then, it's just as basic as we've just said it there. You'll find me in this particular session going very basic, because most times we want to get straight down into the technical bit and all of that. But then if you don't understand the real details and basis of most things, you end up getting into very much technical and then going back to learn. And it's a lot of process going back and forth, which some of us have been unfortunate to go through. And that's why I will sound so very basic as much as possible. Now, having gotten a very simple idea of what clustering is, we'll dive a bit into it. Now, like I said, clustering is just literally the natural grouping of data. It's, automatically grouping data into the natural form, separating data based on their natural form. It's typically an unsupervised learning approach to machine learning. Like I said, in the case of supervised learning, you're talking about having fed a data with the features, which is the dependent variable, and you use that to get, with the features with the independent variable, and you use that to get your dependent variable, which obviously you extract out of your figure. A simple look at the linear regression, y equals ax plus c, tells you that y is what you're looking for, and you have supplied y with a lot of variables that helps you to predict at different intervals. Then you now feed it with a new set of independent variable to be able to get your y. That's literally what you do in your supervised learning, because you've told the algorithm, the model, this is what you at this particular data set of independent variable, this is the corresponding value of independent variable. At this particular, this is the corresponding value. But with unsupervised learning, like I said with rice, you just literally tell a child, I want you to separate this. You didn't tell the child what necessarily the area of separation is. And the child has to look at what is the similarity between these items and what are the differences. It's literally separating items from their similarity and differences. You are not supervising the child. You're not telling the child what to do. But the child use their inner sense to see, rice looks alike, let me remove this. Beans looks alike, let me remove this. And that's just all it is. So it's like the third definition literally puts is the group. It means grouping things which are similar or have common features. They become separate clusters based on their similarity, and the differences is what makes them different clusters as well. So from what we have in the tiny bit of scatter plot that you have there, you could tell from plot A, from just looking at it, you cannot exactly say what cluster does each item belong in, because it looks like everything is together. But then if you look at the bits, a bit clustered differently, and then there's an obvious space between them. You can literally tell that, okay, it's like this one. From the layman knowledge, it's like this upper part, they are very similar, they're the same, and then these ones are probably the same. This is how you get differences based on their common features or similarity to be able to form clusters. You could tell that these are two clusters here. Now a bit more into it. Now from the picture you have here, apart from the position, you cannot exactly tell the difference in terms of clustering, because it's unsupervised. Like we said, you have to be the one to label after clustering, which is, for example, what you now have here. I mean, you have green here, you have blue here, you have purple. This is the labeling coming after the clustering, as against you having a data set that is fully clustered. Now we dive a bit deeper into the actual thing here. The first thing you will look at here is that we're looking at clustering algorithm, and we're looking at basically 5 different kinds of clustering algorithm. There are tons of examples. I mean, if you go to some other resources, you could even have 10 of different distributions on that here. But as it were, we're going to look at just 5, and because of the time limits. And we're not really going to go into details as to the different area. We're just going to look at about 3 k-means, which is a very, very popular form of clustering, and then we'll look at the 2 basic different of hierarchical clustering eventually. Now, what we can tell is this: we have, from what we're looking at, we have 5 different kind of algorithm, clustering algorithm. We have the partitioning, we have the hierarchical, we have the density based, we have the grid based, and we have the model based. You could tell from the names that probably a clear inclination as to what each one starts from. I mean, partitioning obviously gets properly partitioned or separated. Hierarchy looks like the diagram we're looking at. Hierarchy, like you have your family tree from your great-great-great-grandfather, and then it goes to the different children you have, and then the different children till it gets to you. That's what your hierarchical clustering. Again, like I said, I'll keep using very, very, very popular example that might even go away from machine learning at times, just for us to soak in the concept. And the density base is literally looking at the density of the different clustering and how close each of them are to the separate cluster to be able to determine. Again, grid based divided based on the different grids, and model based is dependent on mathematical what's it called, the mathematical base for the different separation, which we will look at. So under the model base, you're looking at this combining clustering and statistics to be able to properly separate different concepts and get insight and knowledge from what you're looking at. Now, partitioning, like I said, it divides data objects into a number of partitions where each partition represents a cluster. This cluster basically fulfills, it has certain feature. Number 1, each group must contain at least one object, and each object must belong to exactly one group. And a typical example, very known example of this kind of clustering is the k-means. There are different variations of k-means, k-means plus, different variation basically, and which most times I would say it's about knowing the application of these things rather than cramming the different variation and all of that. So basically, and this can also be referred to as the centroid-based clustering. The second one we're talking about is the hierarchical based clustering. Like I said, it's more of separating items based on the different steps or hierarchy to the roots, and it could be in 2 different forms, which we would look at extensively later. It could be as agglomerative, what's it called, hierarchy, which is bottom up. You're literally going from the general and going to the specific, bottom up, and then the divisive is like you're going from top and dividing back to the general, basically. So that's what it is for the 2 ones we have on the picture there on the slide there, and then we move to density based. Like I said, based on as the name goes, density based clustering literally separates based on the regions or density of connective boundary. The clear features here is that they are related to points nearest neighbors, and the cluster that defined as a connected dense component. It could grow into any direction that the density leads to. So it's more I mean, we all know what density is, how dense an item is, and it follows natural pattern to be able to get that. It gives us very arbitrary shape. It will come in any shape depending on what density the cluster gets formed around. And it's the very good thing about density based is it provides natural protection against outlier, because I mean, you just look at, for example, a magnet. It's more of a natural shape around what density around each of the cluster, and it's literally helps us to avoid issues of outlier, because literally everything is the closest centroid. That's what they follow. Then the grid based is the clustering is divided into grids, like I said. So it's literally based on pattern and divided into grids. And it's the clear feature here is that it's very fast processing time. It goes through the data set once to compute the statistical value for the grid and able to discretize them along grid 9. Anybody who is probably versed with a bit of engineering would be able to understand discretization along grid lines, which is exactly what this concept goes along. So the accumulated grid data make grid-based clustering independent of the number of data objects. And it's more uniform grids are formed to collect statistical, regional statistical data, basically. Then the model based, like I said, you fit a clustering based on the given data, and as well as the mathematical inference attached to it. So there's assumption that data is generated based on underlying probability distribution, and I mean that helps us to automatically determine the number of clusters based on statistics, and it's considered the outliers, which we generally or popularly refers to as noise, and it helps us to get very robust statistics. The other features, literally, there are two basic types. Like I said before, there's the statistical and there's the neural network. The statistic use probability to determine the number of clusters and which cluster each data point belongs, while the neural network approach uses set of connected input units where each connection has weight associated with it. Apologies, I'm trying to ensure that we keep to time. That's why I'm moving a bit rather fast. Now, K-mean clustering, it's like I said, we're going to look typically at K-means specifically, and then we'll look at hierarchical clustering a bit more deeper. So K-mean clustering is literally a situation where you use n set of observation to determine K amount of clustering. That's literally how the name came about. And the main idea is to define a centroid K, and each cluster is built around that centroid K, and that's literally how it's defined. And these are the steps to go about it. Like I said, you choose a number of clusters, K, and you randomly appoint or assign each data point to a cluster. You repeat, there's a particular step that you keep repeating, you keep iterating until your cluster stops changing. Basically, you've reached the optimum selection of cluster in this case. So what you keep doing is, for a cluster, you compute the number of you compute the centroid by using the mean vector of the points in that particular cluster, and you assign each data point to the cluster for which the centroid is closest. The note, a very important note of caution here is that the scale, you need to scale the variables before you cluster the data, and also you continuously look at the scatter point or the data table to estimate the number of cluster center to set the K parameter. So basically, K-means clustering has a lot of application, but it's usually very much specific when your dimensionality is low, and when you're talking about numeric and continuous data. That's the most effective use case of K-means algorithm. The practical use cases, if you're trying to cluster documents or literally separate the documents in based on the preferred clustering, or you're trying to, this is a particular use case in risk management, in insurance as you were, then risk management. If, for example, an insurance company or a broking firm is trying to discover criminal prone area, like in developed countries like US and UK, there are certain areas where burglary insurance will be more expensive than others, because the proper analysis has been done and they've been able to cluster the different areas based on different crime activities going on there, and be able to say this particular place is probably more prone to crime, car theft, burglary cases, and similar issues. Even police can actually use this kind of concept to solve a lot of crime-related places, to be able to know where to appoint more attention into, by using it to identify crime-prone areas based on inherent attributes to crime. Now, the other thing is the first example I said, which K-means can also be applied to, is a customer segmentation. You segment customer. We all know, I think we should all know rather, that customer segmentation is literally differentiating customers based on their buying characteristics. For example, if you're trying to sell certain product, maybe you're trying to do a mental health app, for example, definitely you might do well if you're targeting age 18 to 21 by putting your advert maybe on TikTok, on LinkedIn, on Twitter rather. But if you're looking at people from the age of 40 upwards, you're looking at maybe Facebook. That's literally you determine the behavior of the customer and where necessarily to find them. So in more corporate setting like banks, insurance, these are the ways to get inherent characteristics of customers and the way they buy, their buying pattern, and that helps you to specifically sell to customer what their tastes are. Imagine someone is about to market to you and is selling what you want in your mind, and then you feel like it's some magic. It's because this person has already clustered the customers in their database and be able to determine their buying pattern, their buying behavior, to know what exactly to give these people. You would not do yourself very well by, maybe you want to sell skinny jeans and then you're selling to people from 45 and above. I mean, you've probably not done your customer segmentation very well. So these are the kind of input that comes out of that. So insurance fraud detection, literally I would say fraud detection generally, and anomaly detection, you can use K-means clustering to achieve a lot of that. But why insurance is probably specifically mentioned is the biggest fraud in Western world is usually perpetrated in insurance, and this helps you to most likely cut off fraudulent activities immediately they start going on. And how do you go about this is, for example, you're able to cluster or to segment the behaviors of different transactions on your book based on their inherent characteristics. And then once the clustering is defined, you're able to label literally a very clear kind of transaction, maybe green, the suspicious one, maybe amber. I mean, the very fraudulent one, maybe red, and all of that. And the moment a transaction seems to be somehow moving around an amber space or red, is getting suspicious, and it's a very, very good way to tackle fraud detection, and which is something. It's one of the areas that people are usually mainly focusing on for outsourcing activities for companies now, because most companies can't even build it in-house, which is just plain K-means clustering that it takes to help you get such results. Public transport data analysis is also something very key. I think we might not be able to relate so much in Nigeria, but then, okay, Lagos State is a typical example. If you're trying to, you wouldn't think that Lagos State just came up with BRT all of a sudden out of the blue, or maybe BRT is running from certain area and doesn't go to Abule Egba, and at some point they must have done some analysis that shows them the challenges in that area and how they can decongest that area to be able to, by the use of public transport. So basically analyzing the public transport data would give different inputs as to what's going on in these different areas, clustering the different areas based on different difficulties on how easy movement of transport are in that area. You can also use K-means clustering to cluster IT alerts. Then we move straight up to hierarchical clustering. The reason we're focusing on them two is literally down to the popularity of the use cases. Now, hierarchical clustering is literally breaking down features to different steps, if I may use that word. You look at your typical family tree, like I said, you go from your great grandfather and then it dissects up till it gets to your grandfather, to you, your father, to you, and then your children if you have one. And that's what an hierarchy looks like. There are two basic ways hierarchical clustering can be done. It could be done bottom up or top bottom. Bottom up is what you have when you have the agglomerative. I always tend to pronounce that somehow. The agglomerative literally is what you call your bottom up, and the divisive is the other way around. It's literally opposite of each other. The divisive starts from the roots. So you're starting from the very top. A typical example is you're doing a root cause analysis. You start from the problem itself and you go to what possibly could have happened, and then you go all the way down like that till you're able to come up with the exact this thing. You can look at a typical decision tree also. Is very similar to what we're looking at here. So basically, for the divisive, you're starting from the root here where you have your A, B, C, D, and apparently based on their similarities and differences, it is clear that A and B are kind of similar and C, D, E are much different, and they got clustered differently, meaning you're starting from the root, which is a single cluster, and then you clustered items differently based on their similarity and differences. And then you further cluster C, D, E to C, which obviously tends to be different again from D and E, and then that gets clustered again, and A and B gets clustered differently, and then you now have 7 cluster, which is A, B, C, D, E. So at the end of the day, each element becomes a cluster of its own at the end. And the other way around is your agglomerative. We start from each element being identified as a single cluster, and then based on whatever similarity they have with other elements, they become combined clusters, like you have A, B, D, E, and then it goes further to cluster again where you have C, D, E, and A, B, C, D. So that's literally what you have with your hierarchical clustering. And like I said, the agglomerative is a very common type of clustering, and it is a bottom up. You treat each object as a single cluster, then you pair them based on their similarity until all cluster have emerged into a single big cluster. So again, we look at it again here. We're starting from the total, all the clusters here. You have the single items individually being represented as cluster, and then GF, based on similarity, becomes a single cluster. DE becomes a single one. BC becomes a single one. And then that goes a step further until you have everything as a single cluster, basically. So we move next again. What are the implementation steps? That's literally what I've explained. You prepare your data. After preparing your data, you compute the dissimilarities between them, and then you use linkage function to group objects into hierarchical cluster tree. Objects that are in close proximity are linked together using linkage function, and you determine where to cut the hierarchical cluster depending on your need, instead of literally, because the simple question would be, why are you going all the way from top down? Depending on your need, you determine where you cut the hierarchical cluster. The divisive is simply the opposite of what we just described. Like I said, it starts from the general and it gets well divided till you get to the specific. The steps are literally opposite of what you have from the agglomerative. Yeah. We've talked about k-means, but in a bit more detail. You choose your, I think that must have been a problem with the slide getting together. That must have been a problem, yeah. So we'd already talked about k-means, so there's no point going through it again. Now, the next thing to talk about is the criterion to benchmark your clustering on. How do you determine what type of cluster to use, clustering algorithm to use, and what are the benchmark to go ahead and benchmark it on? So basically, you know, we've got 7 V's of big data, but in this case, we're just looking at the 3 V's: volume, variety, and velocity. So the volume, these are the things that helps you to determine the kind of clustering you end up using eventually. Volume typically refers to the ability of the clustering algorithm to deal with large number, because volume refers to large numbers, and these criteria are generally considered the size of the data, dimensionality handling, and outlier handling. The variety helps to handle different kind of data sets, be it numerical, categorical, or hierarchical, and the following are considered as well: the type of data set, the cluster shape, and then we'll talk about velocity, which refers to the speed of clustering. It helps to consider the complexity of the algorithm at the runtime, because you will discover that a lot of times we talked about iteration when you're doing clustering. So if the algorithm is too complex or the runtime is too high, you might not have an optimum clustering job. So it's key to look at that. So now the different features to consider under this is when you're looking at the different type of data sets. So clustering works effectively more, not extensively, but more on numerical data, or on purely numerical data, or purely categorical data. It's literally performs more purely when you have mixed data type. The size of data can actually have major effect on your clustering. Some clustering methods are more efficient than others when you deal with small, while some are more efficient when you deal with larger data sets. When you're talking about the input the parameter, fewer parameters literally helps your clustering to have more quality, rather than having larger parameter in practice. Outlier is usually a huge challenge, and it's something you cannot do without, because when you talk about real life data, it's not pure. It's never void of outlier, because it's human being that actually enter these data sets. So it could be wrong from intentional input. It could be wrong from error, actually. And it's literally one of the huge challenges. So if you're dealing with much outliers, you could actually determine to go with the kind of clustering algorithm that helps to take care of outlier a lot better. Like I said, time complexity, because you're going to continuously iterate, it is very, very advisable to have your clustering not take much time, because it becomes impractical when it's taking too long for each iteration and it's something you do continuously. Stability literally refers to the fact that your clustering should be able to deal with data irrespective of the order in which they are being fed into the algorithm. Clustering shape should handle real data and the wide variety of real data sets. Obviously, like we said, in real life, you can't literally determine the purity of data. So it's very, 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 a very key thing, and high dimensionality should be handled effectively. So when with all these characteristics that we literally stated now, this table helps us to know which kind of clustering algorithm you're going to use for different cases. You could see generally when it comes to hierarchical data, the size of data, it's really very effective when the size of data is very, very large across all the different type of hierarchical data. The same with density-based data and the same with grid-based. And you could see that majority of the model-based do not deal well with large data sets, and they do not handle noise very well. So it is very effective and very, very advisable to always try as much as possible to go through the different requirements before deciding on which clustering algorithm method you're using. Typical use cases. For example, if you want typical use cases, you can use clustering to order. You can order a set of clusters with variable precision. If there's a need to have another set of cluster with variable precision, obviously you're going for your hierarchical cluster, and different use cases of hierarchical cluster for this kind of use is, for example, you're trying to get the different stages in a biological process where each stage can be more or less precise. You can see when you're talking about stages, it has to do with hierarchy, with steps, different grade of product where each grade is a cluster. Then you're trying to determine clustering sensor reading on the factory floor where each machine is a cluster, clustering gene according to their function where each function is a cluster, and then an unknown number of cluster. That's another use case. You're trying to determine you're trying to do clustering when you don't literally have you have an unknown number of clusters to look at. So when there are unknown number of clusters, you can get that using X-min, which is literally a variation of K-min algorithm. That's why I said instead of cramming the different kind of algorithm, because it keeps evolving every day, you literally just need to focus on using them and the use cases and be able to do the technical bits. So the use cases for this kind of example is clustering customers according to their spending habits. You don't have a determined number of cluster in mind. Your clustering job would actually get that exposed to you. So also clustering images of animal according to their species. The next one is you can actually cluster if you're required to cluster text data in case of instances where document has to be clusters, and you can go about that using topic modeling, which is a typical use case in NLP. It automatically learns, by NLP, natural language processing, it automatically learns the structure of a document by looking at the word pattern. And the use case is, for example, you want to cluster news article by their topic, or you want to cluster customer review by product that they are reviewing, or clustering blogs by their topics. The next use case is non-elliptic cluster. If you have a case where you need to deal with non-elliptic cluster, which are a group of points that are not well represented by elliptic shape. So basically, they are very irregular, and you can be able to do this using examples like affinity propagation, fractal, and the like. And what are the use cases here? Again, is clustering images according to their shapes. clustering images of animal according to their species, clustering data that contains a lot of noise, and clustering star in galaxy according to their position, or people at a party according to their location. You can see, I mean, from mundane to business to hobbies, the application of clustering ranges very wide. Then the next one is when you have to deal with high dimensional data. High dimensionality cases is when you have so many variables or features. And this type is usually in scientific and research cases. There are many factors that affect different outcome of your research or experiments, and it can be done with k-means plus plus. Like we said, k-means itself is more effective when you have lower dimensionality, but k-means plus plus is more of a variation of k-means that helps to deal with larger dimensionality. And what are the use cases? You're clustering customer based on their spending habits across a large number of products. Like I've given an example of the customer spending pattern, but now you're looking at very large product variation. So that is a very typical use case there. Or you're clustering image of an animal according to their shape and color. Now, the next one is you're trying to work with data with mixed type feature. Again, you see that most of the examples I'm giving are those that we said probably would not work well typically in clustering. So now we said clustering works well with a specific data type, either numeric or categorical. But when you have a situation where it is mixed with categorical and numeric, another variation of k-means, two of them, k-modes or k-prototype, are very effective in this use case. And the use cases for this part of this specific example is clustering customers according to their spending habits across mix of categorical and numerical features, or clustering image of animal due to their shape, color, and size. When data is not literally linearly separable, you can use Gaussian mixture method or Birch. And the use case here, practical use case here, is to cluster data that contains lots of outlier, clustering that is generated from non-linear process. And the last two, I believe, soft membership in cluster, when there are data point that belongs to more than one cluster with a certain degree of probability. Again, you can use the Gaussian mixture model, the fuzzy C-mean. That's literally a combination of fuzzy logic and your clustering, basically, then the possibilistic C-mean. So the use case here is clustering customers according to their spending habits, where each customer belongs to multiple clusters. So it's not a case of one person belonging to a single cluster, but you can appear in different clusters, or clustering images of animals according to their shapes, color, size, where each image can belong to multiple clusters. And finally, when you have a situation where data is in form of a graph, data in form of a graph can use clustering algorithm like Markov clustering or community detection algorithm. So basically, the use case here, you're trying to cluster social media users according to their interests, or clustering web pages according to their content. And I hope I did justice at minimal time. Thank you.
Thank you, Mr. Ayaya, for that splendid lecture. I would have loved him to continue tonight for, but unfortunately, time isn't on our side. So I'm sure our participants also learned one or two things from today's session. So it's time for Q&A. Drop your questions and I will do well to read them to our facilitator. So I'll be expecting your questions in the chat session right now. So let's go, Q&A. Okay, for those asking about the video will be available after the class, definitely on our YouTube channel. So don't worry. Just go to our YouTube channel. My colleague here will drop the link to our YouTube channel in the chat section. So are you telling me that you understood what our facilitator talked about today? No question or questions? Okay, would there be hands-on session? I don't know. Mr. Yahaya, would there be a hands-on session?
I mean, that could be planned for some other session. It wasn't part of the plan for this session, but we could actually arrange that for some other session. It's actually a very interesting topic, and it will be interesting to have an actual hands-on session. I don't know, it depends on what the calendar looks like.
Okay. At what point do we use clustering? Hello? At what point do we use clustering?
Oh, I was actually talking. I didn't know I muted myself again.
Oh, all right.
So I mentioned it at the beginning. You know, typically when you have cases where you've got data points and they are not labeled, and you need to make informed decisions out of them. For example, I mean, the typical example I gave that time was in the basic way, somebody just pour rice and beans together and tell its 10-year-old child to separate. So it's just instinctively clustering based on their natural behavior and order to be able to separate based on your features, natural behavior and order. And a lot of examples we've given, I mean, a typical most popular example in practice is usually when you're trying to check anomaly detection in case of fraud detection, and also in cases where you're trying to check, which is the most popular use case that I know, customer purchase behavior. You have data of purchases from customer and all of that, and from the merely looking at the data, you can't really tell which is which. So you need to cluster them based on the behavior to determine and to be able to actually have bespoke product delivery to satisfy such customers. I don't know if that makes sense.
All right, sir. What's your take on data that are not scaled?
Well, I mean, the best practice, you would obviously want to do your machine learning. I always say is more of an art than than science, knowing your ways around it. And when you're talking about best practice, you obviously have to scale your data before I mean applying to your model. Basically, it's always the best practice for me.
All right. Someone asked, how can missing values be treated in clustering process?
How can missing value?
Yes, be treated in clustering process.
Basically, if you want to look at it in essence, unlike your normal regression and your classification model, you obviously, I mean, just like your regression and classification model, you obviously start any machine learning from treating your data, cleaning your data and all of that. And missing value treatment, there are a variety of ways of treating missing value. It depends on how the missing value arrives, and you have tons of ways. It's not a one approach fix all for missing value, literally. There are tons of ways to treat missing value, and it's determined by how you're able to analyze the missing value and how the missing value itself came across. There's no one single approach fix all. Some people, depending on how, I mean, if the missing value are not so much, you could probably allocate average. In some cases, you could even delete and all of that. There are many ways to treat missing value.
Okay, then let me just take the last question because time is not on our side. Someone said you should. Okay, let me ask this one. What are some of the basic approaches for cluster interpretation, especially after the data has been scaled and it's difficult to make relationships to the original data? I know, should I read it again?
Yeah, I'm finding it a bit hard to get that question. Maybe the person can message me personally.
Okay, all right. Then finally, I don't know, this person did not really write it correctly. Big data, I don't know.
Yeah, I think the person is making a reference to something that I said earlier. It's literally the same thing like your marketing mix. You hear the some will tell you it's 7, some will tell you it's 3, some will tell you it's 5. There are actually 7 V's of big data, not just 3. But in this case, we just literally referred to the 3. So it's the 7 V's you're talking about: volume, velocity, variety, variability, veracity, visualization, and value. So there are actually 7 V's of big data, not 3. But I mean, we focused on 3 here. The most popular ones are actually the 3 we focused on. So partially you might be right, but it doesn't mean they are limited to that.
Oh, all right. Someone asked that what areas can one apply clustering to NLP?
We talked about something on topic modeling towards the end of the presentation. Let me just 1 second. Yeah, like when you're trying to cluster text data basically, and you apply it to clustering modeling and topic modeling, and typical use cases that we mentioned was clustering news articles based on their topics, clustering customer review by the product they are reviewing, and clustering blog posts by their topics. Those are some topic popular use cases of clustering in using NLP.
All right, all right. Thank you very much, Mr. Yahaya. Someone asked that you should throw more lights on K-means clustering. K-means clustering.
I mean, I try to be as basic as possible. If maybe the person can again get in touch for so more understanding, but literally, I mean, you choose the number of clustering you want to use, which literally your K. I mean, that's where the K-means come from. You randomly assign each data point to a cluster, and then for each cluster, you compute the centroid, which is done by using the mean vector point of the cluster, and you assign data points that are closest to that centroid. You continue repeating this until your cluster stops. That's literally K-means clustering in a nutshell. But if the person, the person can message me on LinkedIn or Twitter to talk about more.
All right. Thank you, Mr. Hyatt. Thank you very much for this wonderful session. Someone that was asking me that what is he gaining from DSN? I'm trying to tell you that you're definitely going to gain a lot.
What am I gaining? Hello?
Sessions like this, our research sessions, links to our communities, DSN ladies group, research group, just kindly join. And our YouTube link, don't worry, it will also be sent into the chat section. Thank you very much once again, everyone, for joining this session. Thank you, Mr. Yahaya, again, once again. Thank you very much, everyone. My colleagues here will share the links that you have been asking for our YouTube channel. It will be sent to the chat section right now, right? Thank you very much, everyone.
Thanks, everyone, for having me. Thank you, DSN, as always.
Please kindly give us just a few minutes before the link is sent. Okay. Okay, I'm coming. All right, it has been sent to the chat section now. So don't worry, the recorded video will be sent, will be uploaded. So kindly check it out and watch. Thank you very much once again, and have a splendid weekend.